Sometimes one dot structure is not enough to completely describe a molecule or an ion. Sometimes you need two or more. And here's an example. This is the acetate anion, and this dot structure does not completely describe the acetate anion. We need to draw a resonance structure, another resonance structure. And so what we're going to do is take a lone pair of electrons from this oxygen and move that lone pair of electrons in here to form a double bond between this carbon and that oxygen. At the same time, we're going to take these two pi electrons here and move those pi electrons out onto the top oxygen. So let's go ahead and draw a resonance double-headed arrow here. And when you're drawing resonance structures, you usually put in brackets. Let's go ahead and draw the other resonance structure. So now there would be a double bond between this carbon and this oxygen here. This oxygen on the bottom right used to have 3 lone pairs of electrons around it. Now it only has 2 because one of those lone pairs moved in to form that pi bond. The oxygen on the top used to have a double bond. Right now it has only a single bond to it, and it used to have 2 lone pairs of electrons, and now it has 3 lone pairs of electrons. That gives the top oxygen a -1 formal charge, and make sure you understand formal charges before you get into drawing resonance structures. So it's extremely important to understand that. All right, so next, let's follow those electrons just to make sure we know what happened here. So these electrons in magenta, right, moved in here to form our pi bond like that. And the electrons over here in blue, right, moved out onto the top oxygen. So let's say those electrons in blue are these electrons like that. So we have 2 resonance structures for the acetate anion, and neither of these structures completely describes the acetate anion. We need to draw a hybrid of these 2. And so if we take a look at, let's say, the oxygen on the bottom right here, we can see there's a single bond between this carbon and this oxygen. If we look at this one over here, we see there's now a double bond between that carbon and the oxygen. So if we think about a hybrid of these 2 resonance structures, let's go ahead and draw it in here. We can't just draw a single bond between the carbon and that oxygen. There's some partial double bond character there. So it's a hybrid of the 2 structures above. So let's go ahead and draw in a partial bond here, like that. The exact same thing for the top oxygen. Here we have a double bond, and then over here we have a single bond. So somewhere in between, right? So in between is going to be our hybrid. So let's go ahead and draw that in. So we can't just draw a single bond in our hybrid. We have to show some partial double bond character, drawing the dotted line in there like that. And also charge, right? So if we think about charge, the negative charge is on the oxygen on the bottom right, and then over here the negative charge is on the top oxygen. And so that negative charge is actually delocalized, right? So it's not localized to one oxygen, it's delocalized, it's distributed evenly over both of those oxygens here. And so this is just one way to represent the hybrid here. And studies have shown that the hybrid is closer to what the actual anion looks like. So studies have been done on these bond lengths here, and the bonding between this carbon and this oxygen, it turns out to be the exact same bond length as the bond between the carbon and this oxygen. So it's the exact same bond length, and so the hybrid, again, is a better picture of what the anion actually looks like. Let's think about what would happen if we just moved the electrons in magenta in. So if I go back to the very first thing I talked about, and you're like, well, why didn't we just stop after moving these electrons in magenta? Let's go ahead and draw what we would have if we stopped after moving the electrons in magenta. So we would have this. So the electrons in magenta moved in here to form our double bond. Right? And if we don't push off those electrons in blue, this might be our resonance structure. The problem with this one is, of course, the fact that this carbon here has 5 bonds to it. So 1, 2, 3, 4, 5. So 5 bonds, so 10 electrons around it. We know that carbon can't exceed the octet of electrons because of its position on the periodic table. So this is not a valid structure. And so this is one of the patterns that we're going to be talking about in the next video. So the pattern is a lone pair of electrons, right? So next to a pi bond, which is the example we see here for the acetate anion. And so these are the 2 resonance structures. The problem with the word resonance is when you're a student, you might think that the anion will resonate back and forth between this one and this one. That's just kind of what the name seems to imply. And that's not actually what's happening. It's just that we can't draw, if we're just drawing one dot structure, this is not an accurate description. And so the electrons are actually delocalized. So it's not resonating back and forth. When you draw resonance structures in your head, think about what that means for the hybrid and how the resonance structures would contribute to the overall hybrid. So don't forget about your brackets and your double-headed arrows and also your formal charges. So you have to put those in when you're drawing your resonance structures. All right, let's look at an application of the acetate anion here and the resonance structures that we can draw. So if we look at the acetate anion, so we just talked about the fact that one of these lone pairs here, so this is not localized to the oxygen, it's delocalized, so we can move those electrons in here, we push those electrons off onto the oxygen, and we can draw a resonance structure, and so this -1 formal charge is not localized to this oxygen, it's delocalized. And so because we can spread out some of that negative charge, that increases the stability of the anion here. So this is relatively stable, so increased stability due to delocalization. Right? So the fact that we can draw an extra resonance structure means that the anion has been stabilized. And so this is called pushing electrons, right? So we're moving electrons around, and it's extremely important to feel comfortable with moving electrons around and being able to follow them. So the only way to do this is to get good at this is to do a lot of practice problems. So please do that. Do lots of practice problems in your textbook. If we compare that to the ethoxide anion, so over here, right? If we try to do the same thing, if we try to take a lone pair of electrons on this oxygen and move it into here, we can't do that because this carbon right here already has 4 bonds, right? So it's already bonded to 2 hydrogens, and then we have this bond and this bond. And so moving those electrons in, trying to delocalize those electrons would give us 5 bonds to carbon. So we can't do that. We can't draw a resonance structure for the ethoxide anion. So those electrons are localized to this oxygen. And so this oxygen has a full -1 formal charge. And since we can't spread out that negative charge, right, it's going to destabilize this anion. Right, so this is not as stable, so decreased stability compared to the anion on the left because we can't draw a resonance structure. If we think about the conjugate acids to these bases, right? So the conjugate acid to the acetate anion would be, of course, acetic acid. So we go ahead and draw in acetic acid like that. The conjugate acid to the ethoxide anion would, of course, be ethanol. So we go ahead and draw in ethanol. And we think about which one of those is more acidic, right? We know that acetic acid is more acidic. It's more likely to donate a proton because the conjugate base is more stable because of, you could think about resonance, right? Or delocalization of electrons. If you're looking at ethanol, ethanol is not as likely to donate its proton because the conjugate base, the ethoxide anion, is not as stable because you can't draw any resonance structures for it. The negative charge is not able to be delocalized. It's localized to that oxygen. So this is just one application of thinking about resonance structures. And again, do lots of practice. In the next video, we'll talk about different patterns that you can look for. And we talked about one in this video. We took a lone pair of electrons, so right here in green, right? And we noticed this lone pair of electrons was next to a pi bond, and so we were able to draw another resonance structure for it. We don't have that situation with ethoxide. We have a lone pair of electrons, right? But we don't have a pi bond next to it. And so again, more in the next video on that.